Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. In this video, we're going to continue our discussion about rational functions. You should have already seen my video on review of rational functions, kind of their definitions and whatnot. You should have also looked at my video on finding domains of rational functions and identifying vertical asymptotes of rational functions. In this video, it's somewhat a longer video because of the fact that horizontal asymptotes, there are options. And so because of that, we spend a little bit more time developing those options. So we'll dive right into it here. We're going to use Desmos to build a table of values and investigate the possible horizontal asymptotes of the following functions. I'm doing this as a Desmos investigation mainly because it's a good way to really showcase how to use Desmos, one, and the results of certain patterns with rational functions. So here are the three functions, and yes, I could easily use Desmos to graph them, but that's a bit of a cheat here. I don't want to cheat. Ooh, I can widen this out. Let's do that. I don't want to cheat because I would like this to be more of a table investigation. So let's go ahead and add a table here, Desmos. And I should have shown you how I did that. Let me scroll up a little bit. So I hit the plus sign, and one of the options is to add a table. And then Desmos automatically creates a table of x1 to y1. The x values are called x1. The y values are called y sub 1. And I don't want my y values to be y sub 1. Instead, I want them to be f of x sub 1. Again, if I haven't said it in this course, x sub 1, the sub there, is shift minus sign on your keyboard. Now I want to see what happens as x goes to infinity because we're looking at the horizontal asymptotes. So I'll let x equal 10, and then 100, and then 1000, and so on and so forth, right? So you get the idea here. Those numbers are getting incredibly small. You could also do the negative version of them. So negative 10 and negative 100 and negative 1000, right? And the same thing's happening, that the y values or the function values are tending to the same number, which is 0. Both of the outputs are both tending to 0, whether you're going to positive infinity or negative infinity. So let's go ahead and write that in for this function right here. I'll just say the horizontal asymptote is y equals 0. Because again, the y values as x went to infinity and negative infinity, in fact, the y values tended to a height of 0. Now going back to our table here, I'm going to replace f with g. In fact, I'm just going to move that table down so you can see g of x here. The only difference between f and g is that f did not have an extra little x in that numerator. G does. So let's see if I switch the function name to g. Look how nice it is because the table just auto-generates itself at this point. As the x values get fairly large, you can see the y values tend to they tend to the height of 3. Again, as the x values go to negative infinity, or as they get very negative large, the y values again tend to a height of 3. So this is fairly convincing that there's a horizontal asymptote at y equals 3. And I just realized as I came back to this page that it was not updating what I was writing last time, but luckily I caught up here. So in this case, the very middle function g of x has a horizontal asymptote, again, at y equals 3. As x's get very negative or very positive, it seems like the y values were tending to 3. And we're going to discuss why that's the case in a moment. Now the very last function, h of x here, the only difference between that and the previous functions, again, is this extra little power on x. This f had x to the 0th, g had x to the 1st, and h had x to the 2nd. So let's take a look at what happens in that case. Here we are back at the Desmos screen, and I just moved our table down so that we could see h above, and I'm going to trade out this function name for h. Now as x gets really large, 10, 100, 1000, and then 10,000, you see the y values are actually getting large. They're just blowing up. And if you're not 100% sure, if you say, well, it looks like it's going to 30,000, just add another 0, or yet another 0, or another one, or another one. These numbers are getting huge, so it seems to be going to infinity. Y values are getting huge, so as x goes to infinity, y goes to infinity, which is pretty convincing that there's not a horizontal asymptote in the positive infinite direction. But what about the negative infinite direction? Well, you can see, same thing. Negative 10 leads to negative roughly 40. Negative 100 leads to roughly negative 300. Negative 1000 as an input leads to roughly negative 3000 as an output. Negative 10,000 as an input leads to negative 30,000 roughly as an output. So it looks like those are going to negative infinity. Since the y values are neither in either direction, since the y values are not approaching something finite, there's not a horizontal asymptote for h of x. So I'm going to say horizontal asymptote, whoops, except I don't want the highlighter to say that. I want to use pen here. So the horizontal asymptote, I'm going to write none. This is a very special case though, because there is an asymptote there. It's just not a horizontal asymptote. But as I mentioned in one of the first or second video in the series, those special asymptotes we'll talk about a little bit later. So this theorem actually summarizes what we've just seen, and we'll go back to what we've just seen just to kind of justify this theorem a little bit. So we're going to let our rational function just be a numerator function over a denominator function. They're both polynomials, okay? And the degree of the numerator we're going to say is lowercase n, and the degree of the denominator we'll call lowercase d. There are three cases. Either the degree of the numerator is less than the degree of the denominator, or the degrees of the numerator and the denominator match, or the degree of the numerator is greater than the degree of the denominator. That's it, right? Those are the three realities. Either they're the same, or one's bigger than the other, or one's less than the other. That's just the reality of how inequalities work. And what this theorem is telling us is if the degree of the numerator is strictly less than the degree of the denominator, then the function has a horizontal asymptote at y equals 0. Well, let's hop back. Notice in part A, the degree of the numerator is actually 4th degree, right? If you were to multiply everything out, you would have this 2nd degree polynomial times a 2nd degree polynomial. It'd be 4th degree. Whereas the denominator is of degree 5. So numerator has total degree of 4, and the denominator has a total degree of 5. So the numerator has less power than the denominator, and therefore it turned out that our horizontal asymptote was 0, and it's just not showing up on my screen. There it goes. So that is a good, not proof, but a justification. And here's how I've always thought about it since I was a student. If there's more power in the denominator, then as x goes to infinity, really, it's not a tie between the numerator and the denominator. The numerator is roughly x to the 4th. The denominator is roughly x to the 5th, which is, again, roughly 1 over x. Well, as x gets massive, think about 1 over a massive number, 1/1,000,000,000th. Well, man, that's hardly anything. It's basically 0. And that's exactly why the horizontal asymptote is going to be 0 in this case. Because essentially these polynomials are degree 4 over degree 5, which is roughly a 1 over x situation. And as x goes to positive or negative infinity, that number is going to tend to 0. It's not a proof, It's a verbal justification. Now let's take a look at the second case. If our degrees are the same between the numerator and the denominator, then the function still has a horizontal asymptote, but it's at this line, y equals a over b, where a is the leading coefficient of the numerator and b is the leading coefficient of the denominator. And that's kind of a hard one to kind of imagine, but actually when you see it in action, it's not too terrible. For example, take g of x. The degree of the numerator, well, let's see, I have an x to the first, and then I have an x squared, and then I have an x squared. So therefore, I have 5 powers of x in that numerator. I'm going to point at that numerator and just say degree 5. The denominator hasn't changed, so that's also degree 5. So there's a tie between the numerator and denominator for the absolute degree. Well, everything else is kind of fluff, honestly. When you have a 5th degree polynomial, all the smaller degree components really don't mean very much when x gets huge, whether it's positive infinity or negative infinity. So really this this rational function, I'm going to write it over here, is approximately, as x gets massive, like an x to the 5th over an x to the 5th. However, you have to look at the coefficients of each of these pieces. 1 times 1 times 3. 1 times 1. So the numerator is not actually an x to the 5th, it's a 3 x to the 5th. The denominator is a 1 x to the 5th in the long run. And if you do that cancellation, that's just 3. X to the 5ths cancel. And so over the long haul, the horizontal asymptote is y equals 3. Again, same argument. Over here, it's just not as easy to see because you have to imagine that this denominator is tending to infinity. But it's much easier to see when you can just cancel x to the 5th over x to the 5th. It's just the leading coefficients, had you multiplied out those polynomials. Now, the very last condition, if the degree of the numerator is greater than the degree of the denominator, that tends to be a brand new topic for everybody. Most people have not seen that if they're in a trig class. So if the degree of the numerator is greater than the degree of the denominator, the function has either a slant asymptote or an oblique asymptote. Don't worry about the n equals d plus 1 or greater than d plus 1. That's just me being rigorous. The reality is it has an asymptote, but the asymptote is not a horizontal line. It's like some either slant, like y equals mx plus b, or it might be oblique. An oblique is just essentially a different function, like a parabola or something like that. Now, asymptotes are just guidelines to graphing, and so you would just graph these oblique or slant asymptotes to help you graph. To be very honest with you, in a trig/college algebra course, we do not deal with oblique asymptotes. That is a pre-calculus topic. But we do deal with slant asymptotes. So we will deal with that in a little bit. I'm not going to really sweat it right now. And also, I have the word proof here as if I'm going to prove this, but I don't want to. I don't want to burn the time on proving this when it's not really that entertaining of a proof. Maybe I'll do it at the very end if I have time, but I don't really want to. So there you go. Now let's take a look at this. Without using technology, state the horizontal asymptotes of the following functions. Without using technology. So now we're not allowed to use Desmos. Well, if you take a look at f of x here, the degree of the numerator is 2. The degree of the denominator is 3. So that the denominator has more power. So you could say, this is not exactly, but over the long haul, it roughly mimics 3x squared over 1x cubed, which is 3 over x, which tends to 0 as x gets massive. It's like saying 3 over a trillion. Well, 3 trillionths is nothing. So this has a horizontal asymptote at y equals 0. I'm just going to write HA, y equals 0. On the other hand, g of x, Well, this is over the long haul, roughly 3x cubed over x cubed, which is equal to 3. So I know over the long haul, not in the short term, but when x is massive, whether it's positive or negative, this function g of x will tend to a height of 3. So the horizontal asymptote here is y equals 3. So that is a good review, in a way, of horizontal asymptotes. And I hopped back here because I thought maybe I'll do that proof, but I actually just don't want to do the proof. I just don't feel the need to. So we'll go ahead and stop this video now and move on.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.